Now we're going back to our previous equations. This gives that energy density would be equal to 1 over C. These were the original definition. Pi over C. Between cosine theta. Okay. So now the I new density would be cosine theta over 40. Or other terms as well, other quantities like flux, F nu. This was the original definition for that. It's I nu cosine theta d omega, the general definition, and this too can be written as 2 pi times integration of I nu mu. This is pretty, I guess, obvious, right? I'm just converting cosine theta into mu. That's all. That's all I'm doing. Let's call this equation 41. You can do this for radiation pressure, which is 1 over C. I nu cosine square theta d omega. This would be 2 pi over C. This goes from -1 to +1. The I nu square d mu. This would be equation number 42. Right. So we're going to substitute by substituting equation number 39 in 40, 41, and 42. You can write down U nu equal to 4 pi over C. B nu, I'll just put B nu, okay? B nu would be a function of optical depth, just to so that everything's clean. I'm just going to keep it like that. Let's call this equation number 43. And similarly, you can write down the flux would be equal to 4 pi over 3. The B nu, D nu is equation number 44. And then P nu. This comes from the integrations of equations 40, 41, and 42. You had to do the integration yourself, okay? I'm just going to write down the results. Is 4 pi over 3c times P nu. And let's say this is equation number 45. Okay. And if we divide equation number 44 by 43, you end up with an expression like this: dB over d tau divided by B nu. And this would be roughly equal to 3 F nu divided by C nu. And if you, by earlier reference, this would be an isotropic term, and this would be the isotropic term. Okay, right. Oops. Say that this ratio, which is F, flux divided by energy density, which are dependent on frequencies. Let's say this, we just integrate of all wavelengths or frequencies, so that we're going to replace this by just f divided by u. Okay, so this is by equating of all frequencies. Right, so we end up with then. Okay, I'm going to rewrite the previous equation in this way. So it's the anisotropic term divided by the isotropic term, which would be roughly equal to 3 times the flux divided by E times the density. Call this equation number 46. And also we know that the total energy density of black body radiation would be equal to AT4 we got something like that. Let's call this equation number 47. I don't remember what I put here. It's simple A or a subscript B, something like that. Okay, I'll just keep it like that, okay? A of B. And also we know that the total flux emerging from, emerging out of the surface, emerging out of the surface. Okay, let me write it down. Write it. Emerging out of the surface. And this is given by Stefan Boltzmann law. This comes from Stefan Boltzmann law. We can say it's F is equal to the flux, the total flux, equal to sigma E4. Okay, I'm going to put a subscript here, EFF, which means effective. This is the effective temperature, which means, okay, this is what we mean by effective temperature. This is the effective temperature at the surface, or let's say off the surface. Also, it must be noted that sigma is equal to CA by 4. This is not brand new information, but I'm just going to put an equation number for that. Okay, CAB. The previous term. Okay. So this means that we can write down the previous equation in this way. The anisotropic divided by the isotropic would be roughly equal to T divided by 4. You should be able to do this math yourself. Okay, I've just made some substitutions. That's all. The effective temperature divided by temperature to the power 4. Let's call this equation number 50. So again, T effective temperature, or the T effective means the temperature, whatever the temperature that is at the surface. Okay, I just want to distinguish that from the general temperature. That's why I put it as T EFF. Now, interestingly, as you go deeper in a stellar atmosphere, the temperature is going to increase. The temperature is going to be actually pretty much higher than the effective temperature. This is, as you know, this is the case for the sun, as an example. So it's going to be that, which means if you go back to that equation, the equation number 50, you can see that this equation roughly becomes, it's going to be nearly 0, right? This is this ratio to the power 4, which means it's going to be pretty much 0. Which, in other words, it means that the anisotropic term is negligible as you go deeper into the atmosphere. Okay. Becomes negligible. So inside the atmosphere, that means inside in the sense deep inside the atmosphere, the radiation field is mainly, is nearly isotropic in deep layers of a stellar atmosphere. Okay, right. That's about it. Anyway, this is quite a mathematical description of what we have to expect deep inside an atmosphere, in a stellar atmosphere. Okay. Now, as I've told you many times, you have to go back and forth between all these equations and see if what I'm saying is actually true, and if I've done any mistakes in the algebra, basically. Okay. And if you find any, you have to ask these. You have to make sure that you clear those things from me. Any doubts or any problems? Okay. Right. Now this allows us to go to the next topic. For the gray atmosphere. Okay. Let me write it down. If alpha nu is constant, for all frequencies Remember, alpha stands for the absorption coefficient. So this is, if this is constant for all frequencies, such an atmosphere is called a gray atmosphere. Okay, I guess that's a pretty straight definition, right? Straightforward definition. So, which means this is, you can just say alpha nu is alpha because it's independent of frequency. If that is the case, then you can also include that the optical depth. If you go back to the definition of optical depth, you will see that it depends on alpha, or it's a function of alpha. So you can say that it's also independent of frequency. And this allows us to write down a previously written equation. I'm not going to put the equation number. This is sort of a very standard equation that we have used before. So this allows us to get rid of all these frequency terms. That's the point, basically. Okay, it's not a new equation. It's it's the same equation we've had before. Just no new terms. Just to be clear, that's the I is when I's nu is integrated all frequencies, and also S is when the source function is integrated all frequencies. Okay. Okay. So similarly, you can write down that the energy density is equal to 2 pi d. Okay, and the flux d 2 pi. I'm just getting rid of those new. Okay, that's the only difference that we have here. And also radiation pressure would be 2 pi d. Pi plus 1. And let's call all these three equations equation number 52. Right, now we go to a new definition. Well, this is not actually a new definition. We have done this before. I think we did it on the very first day of our discussion on radiation, but just rewriting it, definition. J, it's the average specific intensity. Just to refresh our memory, average specific intensity. Right. And we had written down an equation before, and it comes down to this equation here. ID mu and also it would be equal to C over 4 pi times energy density. Okay, we have done this before. So anyway, let's call this equation 53A. And this equation 53B. Okay, together we call it these two equation number 53. Anyway, you might use both maybe just one. Let's say. And if we multiply equation 51 by half and integrate over mu, and on top of that, if you use equation 2, now you're going to have to do this yourself. I'm just going to write the solution. Okay, I've done this myself, so I'm not going to waste any time doing it myself. But this is what you're going to get. df by d tau equal to j minus s. All right, so please check this for yourself. And multiplying equation 51 by 2 pi mu over c, and integrating over mu, you're going to get something like this: dp or d tau equals f divided by c. Let's call this question number 55.